Hey guys, and welcome to another video from the Waste Tutor. In this video we're going to be extending what we kind of covered in trigonometry and circular measure to trigonometric functions. So this is the tie-in specifically to the functions topic, and it's also why I introduced trigonometry here rather than at the start of the course. So this is video 8 of the functions topic. So let's get straight into the unit overview. So the first thing I'm going to do is I'm going to recap the unit circle definition that we covered in the previous video, have a look at some of the exact values using the God triangles that I also introduced in that previous video, and which are necessary to graphing trigonometric functions on a set of axes. Then I'm going to be having a look at how the unit circle definition translates into a sine, cosine, and tan graph on a set of Cartesian axes. And after we've graphed those functions, I'm going to have a look at how we can transform them by changing amplitude, period, introducing phase shifts or vertical translations, for example. Then I'm going to be having a look at some algebraic relationships between sine and cosine, and some trigonometric properties that allow us to expand the sum or difference of several different angles. I'll also then have a quick look at contexts where we can model trigonometric functions. I won't go into that in detail, but I'll just introduce some of those as possibilities, and I will leave using the class pad up to you. Hopefully you cover that in your classes. If you do need any help with that, make sure you leave a comment, and then I can have a look and dedicate a video to just using the class pad for different topics and methods at the end in the supplementary content. But otherwise, let's get started with the content. Okay, so the first thing I'm going to want to do is I want to recap the unit circle definition of sine, cosine, and tan that we had a look at in the previous video on trigonometry, and I will also examine the concept of periodicity. I'll specifically be using and dealing with sine, cosine, and tan in the context of radians. And if you haven't seen radians, make sure you watch the previous video where I introduce radians, and make sure you've had some practice, because it does take some time to wrap your head around it. I'll then be having a look at some of the exact values of sine, cosine, and tan at integer multiples of pi on 6 and pi on 4 radians. This is really helpful for graphing and finding key points in a graph of these trigonometric functions, and so it's really necessary. And an easy way that I always used was using the God triangles, which I'll introduce again here, and which I introduced in the previous video. So let's start on this stuff. So if we look at our unit circle, we have our unit circle here, and the unit circle is defined as a circle that is centered at the origin and has a radius of 1 unit. So this is our x, this is our y, and we have our origin here at 0, 0. We extend a line up to the circumference of the circle, and this line here forms a angle with the x-axis of theta, and we know that sine and cosine are defined as the x-coordinate. Cosine is defined as the x-coordinate, and sine is defined as the y-coordinate. So if we trace it back here, this is equal to our value for sine theta, and this is equal to our value for cos theta. Okay. And then if we look at our tan graph, the tan graph is defined as the tangent line in the positive x-axis, and we can extend our line up, and our tan value will be equal to the point of intersection between that extended line and the tangent to the circle. Alright, cool. So we know that sine theta is equal to the y-intercept, or the y-coordinate, sorry. Our cos theta is equal to the x-coordinate, and our tan theta is equal to this intersection with the tangent. Now let's take a quick look at radian definitions and exact values. So the one that I generally use here is the God triangles, and these two triangles are these. Commonly, if you're looking at degrees, you know that these are 90 degrees in the case of radians, because pi radians are equal to 180 degrees. We know that pi on 2 radians is 90 degrees. So these are pi on 2 radians. And so I'm hoping you're getting used to using radian notation in this context as well. Now, if we look at this angle, that is normally going to be, this angle here is normally going to be 60 degrees. In the case of radians, 60 degrees is equivalent to pi over 3. This is generally 30 degrees. In the case of radians, pi on 6. The way I like to remember it with 30 degrees and 60 degrees is that the first number swaps in the case of 30 degrees. So 6 goes to 30, whereas 3 goes to 3 here. So 60 degrees is pi on 3, whereas 30 degrees is pi on 6. In the case of 45 degrees, we have these two angles here, and normally they're 45 degrees in the case of degree terminology, but in the case of radian terminology, it's pi over 4. Okay? And so the way I remember it, 45 degrees, specifically in between 30 and 60 degrees, is the 4 at the front goes down to pi on 4. That's just how I remember it. But of course you can also go about converting it using the conversion rule that I introduced in the previous video. But as far as I remember it, 30 degrees, 45 degrees, and 60 degrees, the 6 and the 3 switch places, so this becomes pi on 3 for 60 degrees, whereas 30 degrees switches over pi on 6, so 30 degrees is pi on 6, whereas 45 degrees just goes straight to pi on 4. The 4 and the 4 match up, the 3 goes over here, the 6 goes over here. I don't know if this is helpful at all, but if that doesn't work, you can also use the conversion rule that I introduced in the previous video. Now, these are, of course, definitions only for the case of angles smaller than 90 degrees, but we also want to be able to extend this to angles larger than 90 degrees. So based on this, we already know that our angle for cos theta, sin theta, tan theta, we can calculate each of these. In the case of a graph here, we know that pi on 6, we know pi on 4, and we know pi on 3. And so in this case, we know that for the case of cos theta, pi on 6 is going to be root 3 on 2, sine 1/2, and this one is, 1 on root 3, and so on and so forth. In the case of 0 degrees and pi on 2 degrees, we usually consult the unit circle, but we know generally that cosine of 0 is going to be 1, and sine of 0 is going to be 0, etc. And 90 degrees, cosine of 90 degrees is going to be equal to 0, whereas sine of 90 degrees, or pi on 2, is going to be 1. But the way that we get those definitions is more related to the unit circle. So if we extend this to the unit circle, and we look at our unit circle again, and we have it centered at the origin, we know that at 0 degrees, our sine is going to be equal to 0 because the y coordinate here is 0, whereas my cosine will be equal to 1. And then as I go along the circle, my cosine value decreases, 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 decreases steadily until I reach 0. And as my cosine decreases further, we approach -1 at the minimum, and then we increase back to 0, and then we increase back to 1 for cosine. In the case of sine, what happens is we have our unit circle, initially at 0, increasing up to 1, decreasing back down to 0, decreasing down to -1, and increasing back up to 0. And so in the case of tan, what we have is we have 0 increasing up to infinity because we have our tan line, and eventually we go parallel. Then we suddenly switch to very, very negative because this extends down to the bottom, and then we become less and less negative back to 0, and then we start the exact same cycle again. And parallel, and then suddenly very negative. Okay? Hopefully that makes a little bit of sense. Now, in the case of pi on 6, if we look at our unit circle, a lot of what we do to extend it is related to the symmetry of the unit circle. If we look at pi on 6, and this is pi on 6 degrees, we know that sine pi on 6, based on our God triangle here, is going to be equal to 1 over 2. And so, if we look at our sine value at 180, or pi minus pi on 6 degrees, we know that we have the exact same sine value. Whereas for cosine, we will have the negative, but with the same magnitude. And so we have pi on 6, and this here, angle here, will be pi minus pi on 6, which is 5 pi on 6. And so sine 5 pi on 6 will be equal to sine pi on 6, which is equal to 1/2. And if we look at this angle here, and we have our pi on 6, we can see that it'll have the same magnitude, but negative, so sine of 7 pi on 6, or pi plus pi on 6, will be equal to negative sine pi on 6, which is equal to negative 1/2. For all of these cases, pi on 6 is known as the reference angle, and the reference angle is the angle in the first quadrant of our unit circle. This is our first quadrant. And so if we want to find the exact values of angles larger than 90 degrees, we need to link our angle back to the reference angle in the first quadrant of the unit circle. Okay. The same sort of logic can apply to cosine and tangent, and I leave it up to you to try to figure out how that works as well. Now let's take a look at the graphs of sine, cosine, and tan. So these are the graphs of sine x, cosine x, and tan x on extended domains. I've realized I haven't mentioned this concept of periodicity, but this will be something that I introduce in this slide because it directly relates to how we can extend graphs of sine and cosine functions. So, what periodicity essentially refers to is the fact that a sine or trigonometric function generally will have a repeating unit. So there will be one section where we start getting the exact same pattern of sine values, or the exact same pattern of cosine values, or the exact same pattern of tan values. In the case of sine, our period of our sine function is 2 pi, or 360 degrees, because after 360 degrees, we start exhibiting the same sine patterns. Here we have sine going from 0 up to 1 to, 0 up to 1 to 0 to negative 1, and then back up to 0. And then after 360 degrees, we do the exact same thing. This is the same for cosine. At cosine, we start at 1, go up to 0, then go down to negative 1, then go down back to 0, then go back up to 1. Okay? In the case of tan, our period is pi. And that is because we are looking at extending the tan to this tangent on the right-hand side of our circle. So if we look at it this way, we go up to undefined, go to really negative down here, and back to 0. And then here, we again start the same pattern. Okay? So, in the case of a sine graph, we have our unit circle here. It is centered at the origin. And if we look at our sine graph, our sine values, is we start at 0. So if we had a set of axes like y and x, we have our x-axis, we have our y-axis, and we start at 0. We know that at 0, our angle is equal to 0, y equals sine x. At x equals to 0, we have y equals sine of 0, and sine of 0 is 0 degrees because the y-coordinate is 0. Then we start increasing up to 1. And we reach the maximum of 1 when x equals pi on 2, or 90 degrees. So at x equals pi on 2, we reach the peak of our function. And this is at the point 1. We also should note that at sine pi on 6, or sine 30 degrees, based on our God triangle here, this is pi on 6, we know that at sine pi on 6 we reach 1/2. And so at pi on 6, this is this point pi on 6, we reach the point 1/2. Then if we keep going along the circle, we eventually get back to 0, and the point where we get back to 0 is at pi. And that is this point here. Then at 3 pi on 2, we reach our minimum. 3 pi on 2, or 270 degrees, down here, we reach our minimum, and that is at -1, down here. And then we go back up to y equals 0, or sine of 2 pi equals 0. So as a result, we have a graph, if we connect up the dots, that looks something like this. After 2 pi, I should note that this is when the exact same pattern happens, and you can continue on and on. And similarly here, you can continue on and on. Okay? And so that is the concept of periodicity, the fact that you've got these repeating patterns that go on. Often when you have domains that are set, like you can, for example, be asked to graph a graph of y equals sine x for the period 0 up to 2 pi, in that case you would only graph this black part here. Okay? In the case of y equals cosine x, we have a slightly different graph, and we have our y, our x, we have our origin. If we look here, and we have our y and our x. If we look at cosine, at y equals cos x, at x equals 0, we have cosine of 0, which is equal to 1. This is our maximum value for cosine x. Then, as we increase upwards, we reach cosine of 0 at pi on 2. At pi, we reach -1. At 3 pi on 2, we get back to 0. And at 2 pi, we get back to 1. Here we can see at pi, we reach -1. And at 3 pi on 2, we get back to cosine equals 0. Remember, it is the x coordinate. And then as we increase up again, we get cosine equal to 1. And so we have a -1, the minimum point at pi here. And so we can complete the look of the graph in this way here. Okay? And so we have our cosine graph like this. We can, of course, extend that on as far as we want. And that will keep going. Now, in the case of y equals tan x, we have our unit circle here. We have our tangent line. We have 0, increasing up, 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 up. Eventually we reach infinity. And so if we were to graph this on a set of axes, with this being y, this being x, at tan 0, we have 0, and at tan pi on 2, we are suddenly undefined. And so at undefined points, we have an asymptote, and we can see here as we're approaching pi on 2, this y value is going to be tending towards infinity. So as a result, we go upwards in this direction. Another important point we need to note at in the graph of tan x is the point pi on 4. And that's because if we look at our graph here of 1, 1, and root 2, this being pi on 4, we know that tan pi on 4 is equal to 1. And so this point here will be equal to the point 1. Then if we extend here, we suddenly switch to a really negative number associated with y. And so we start approaching from the bottom. And so as a result, we extend back, and we go further, and eventually we get back to 0. And this point at 0 is at the point pi. So as a result, we have something that looks like this. And so here, we go back up and really positive, and eventually we go back to positive infinity at 3 pi on 2. We go back up, and then at 3 pi on 2 back here, we go back to 0. And so at 2 pi here we have a line like this. And as you can see here, we can see that the period repeats itself after x equals pi. You can see that this section of the graph is the exact same as this section of the graph. And so in the case of tan graphs, if you want to graph it over one period, you would only graph it over one section like this one. Okay? So those are the graphs of sine, cosine, and tan. Now let's take a look at amplitude changes and the graphs of y equals a sine x and a cosine x, as well as more general transformations. So, in the case of an amplitude change, what amplitude refers to is how much a y value is displaced from y equals 0. So in the case of a sine graph like this, we can say the maximum displacement of a y point is up here or down here, right? And this in a normal sine graph is going to be -1, 1, so there's a displacement of 1 in either the positive or the negative direction. And so the amplitude of this graph of sine x is said to be 1. Okay? In the case of cosine, similarly, our normal cosine graph will be maximally displaced at 1 and at -1, and so it has the same amplitude of 1. If we look at our graphs, if we look at the equations associated with those graphs, we have y equals sine x, and we have y equals cos x, and these functions will be bounded by 1 and -1. So they will be from -1 up to 1. And so if we consider these functions individually as bounded by -1 up to 1, we can also introduce a out the front, and this a will cause the bounds to be adjusted to -a up to a. And so as a result, if we graph, for example, 2 sine x, that will be bounded from -2 up to 2. And so if we visualize this on a set of axes, we know that our sine graph will look something like this. It'll have the same period, finish at 2 pi, but it will be maximally displaced at -2 and at 2. And so our amplitude of this graph is going to be equal to 2. More generally, if we're looking at our value a will displace our graph by will change the amplitude of our graph by a factor of a. A graph of y equals a sine x will have amplitude a. If we look at our cosine graph and we graph, for example, y equals 3 cosine x, that would mean we are bounded by -3 up to 3, and the graph would look like something like this, where we start at 3, go down to -3, go back up to 3, over a period of 2 pi. And so we start at 3, we go down to -3, and we go back up to 3 by the end. In the case of tangent graphs, which look like this, we can see that there is no amplitude because our tan graph increases infinitely in both the positive y direction and the negative y direction. It is not associated with an amplitude. Amplitude as a concept only applies to sine and cosine graphs. So we've had a look at amplitude changes then. Now let's take a look at period changes. So as I mentioned with period, a period or periodicity as a concept applies to how long it takes for a trigonometric function to repeat its patterns of values. In the case of sine and cosine, it takes 2 pi or 360 degrees for the function to repeat itself. If we go around, the same patterns occur after 2 pi. And again, so then you go around a second time. In the case of a tan graph, the period is pi because the patterns of values repeat themselves after pi units. In the case of a graph of y equals sine bx, for example, the period of this graph will be given by period equal to 2 pi over b, which is also equivalent. We can also write this as 360 degrees divided by b, should we want to use it in degrees. The more common way of dealing with this, however, is with radians, 2 pi radians. Therefore, if we have a look at y equals to sine 2x, our period of our function will be period equals to 2 pi over 2, which is equal to pi. And as a result, we will look at a graph, and rather than proceeding over a course of 2 pi, this will occur at pi. Alright, and so all the necessary points will be sort of crushed together, or dilated, or contracted, I should say, by a factor of 2. The initial point here, that would be at pi, is now at pi on 2. The maximum point of our sine graph, which normally happens at the point pi on 2, will now be at point pi on 4. And this minimum point that normally happens at 3 pi on 2 will now be at 3 pi over 4. And so if we are trying to introduce a period change to a trigonometric graph, what we generally do is we consider the key points of that trigonometric function and apply the contracting or dilating factor to it. In this case, our contracting factor is a factor of 2. In the case of cosine x, y equals cosine 3x, for example, what happens is we look at our graph, we have our y and our x value. Our cosine graph looks something like this, except now rather than occurring over a period of 2 pi, it occurs over a period of 2 pi over 3. And so these key points get contracted as well. This becomes pi over 3. The 3 pi on 2 now becomes 3 pi over 6, which is pi over 2. And the pi on 2 now becomes pi over 6. And so as a result, we have this contraction by a factor of 3, because our period is now 2 pi over 3, just as I've shown in this graph. This is the graph of y equals cosine 3x, and it'll have an amplitude of 1. This is the graph of y equals sine 2x, which equally will have an amplitude of 1, but a period of pi. In the case of a tan graph, we can also look at a change. We can look at, for example, tan 4x. And if we look at tan 4x, rather than having a period of pi, we will have a period of pi on 4. And so if we look at our graph like this, and we finish it up here, we know that the period here normally is pi. In this case, it's pi on 4. This asymptote is normally associated with the point x equals pi on 2. But because of our contracting factor of 4, it is now pi over 8. Our key points at pi on 4, which is at pi on 4, normally we are equal to 1. Because of this contracting factor, pi on 4 has now converted to pi on 16. Okay? And similarly, this 3 pi on 4, which is normally associated with a tan value equal to -1, will now be at 3 pi on 16. And this point here will be associated with -1. Okay, so we have our tan graph like this. Okay, so now we've had a look at the period graphs, we've looked at amplitude, and now we can have a look at phase shifts, which are known also as horizontal translations. When it comes to horizontal translations, we can have horizontal translations in either the positive or the negative direction, and this will be given by these values as are shown in the syllabus here. And so if we look at y equals cos x take pi on 4, this will refer to a horizontal translation, pi on 4 units, to the right. And so this minus means to the right, whereas if we have cos of x plus pi on 4, this will refer to a horizontal translation or a phase shift of pi on 4 units left. And so if we were to graph y equals cos x take pi on 4, it would look something like this. we would have our point pi on 4 being our starting point that is normally associated with 1. So pi on 4, which is normally at 0, has now been shifted over to pi on 4. My value for pi on 2, which is normally associated with 0, is now at pi on 2 plus pi on 4, so 3 pi on 4. And we have our point 0. Our point here at pi is now at pi plus pi on 4, so 5 pi on 4. And our point, so this is at -1, our point 3 pi on 2 is now at, our point 3 pi on 2 is now at 3 pi on 2 plus pi on 4, which is here 7 pi on 4. And finally, our point 2 pi, which is now translated over to 2 pi plus pi on 4, which is 9 pi on 4. And so it'll look something like this. And so as a result, at the point 0, this will be equal to what is normally at -pi on 4, but what is now translated over to 0. And at -pi on 4, we know that our cos graph will be equal to pi on 4. This is -pi on 4. And so it'll be equal to, based on our God triangle, 1, 1, root 2. This is pi on 4. It'll be equal to 1 over root 2. So cos of -pi on 4 is equal to 1 over root 2. And so at this point here, 1 over root 2. Okay, so that is our graph of the cosine graph of y equals cosine x take pi on 4. A shift of pi on 4 units to the right. And similar concepts can be applied to the sine graph and the tan graph. And I will leave those up to you for reading in your Sadler textbook. When we have a look at our relationships between sine and cosine, this relates directly to this stuff we've talked about on phase shifts. If I draw my graph of sine, it'll look something like this, and my graph of cosine will look something like this. If I consider my two graphs, I can see that they are a phase shift apart. My cosine graph, for example, which starts here, starts on the sine graph at this point right here, right? And so if we consider the sine graph and the cosine graph, we can see that the sine graph is, or this should really be, oh boy, this is not a greatly drawn. Yeah, this is not my best sine and cosine graphs. But anyway, we can see that our sine graph is essentially pi on 2 units shifted to the right of our cosine graph. And so as a result, if we want to draw our sine graph of x, that will be equal to cosine of x minus pi on 2. A shift pi on 2 units to the right. If alternatively we want to graph our cosine graph, that'll be a shift of the sine graph pi on 2 units to the left, x plus pi on 2. Alright, and so there is this relationship between our sine and our cosine graphs based on this function here, this phase shift. Now, let's take a look at the angle sum and angle difference identities. These are two trigonometric identities that are basically just given on your formula sheet, and they allow you to calculate the exact values of some angles that you wouldn't normally be able to. The angle sum and the angle difference identities are as follows. Sine of A plus or minus B is going to be equal to sine A cos B plus or minus cos A sine B, whereas cos A plus or minus B is equal to cos A cos B minus or plus sine A sine B. What these formulas mean is that the plus corresponds to the plus, the minus corresponds to the minus. So if I have a sine of one angle plus another angle, that's going to be equal to sine of the first angle times cos of the second angle plus cos of the first angle times sine of the second angle. In this case, the plus corresponds to the minus, and the minus corresponds to the plus. One example that we can use, sine of 75 degrees. This is an angle that we normally won't be able to solve. However, we can also write this angle as 45 degrees plus 30 degrees, right? And 45 degrees and 30 degrees are two angles we know from our God triangles. 1, 1, root 2. This here is pi on 4. We have 1, 2, root 3, pi on 3, pi on 6. And we can also write that as 45 degrees, 60 degrees, and 30 degrees. And so we know 45 degrees and 30 degrees. We can see that this is a angle sum identity, right? And more specifically, it is the A plus B sine angle identity. This then is equal to sine of the first angle, 45 degrees, times cosine of the second angle, 30 degrees, plus cosine of the first angle multiplied by sine of the second angle. And so as a result, if we evaluate this, we can see that is equal to 1 over root 2 times root 3 over 2 plus cos of 45 degrees is 1 over root 2 based on our God triangle times 1/2 is sine 30 degrees. And so as a result, we end up with 3 on 2 root 2 plus 1 on 2 root 2, which is equal to root 3 plus 1 over 2 root 2. And there are several other ways and several other angles, like 15 degrees can be written as 45 degrees take 30 degrees, 105 degrees could be written as 60 plus 45 degrees if we wanted to. And so there are many different angles that you can actually evaluate using these angle sum and difference identities. And I would have a look at Sadler to revise those as well. Now the last thing I wanted to do is just have a quick look at some contexts that are suitable for modeling trigonometric functions. Some of these cases might show up in your test, for example. A common one I see a lot in WACE exams and tests generally is the case of a Ferris wheel, and you're trying to track a point on a Ferris wheel as you move up and down the Ferris wheel. So you have your Ferris wheel, and your Ferris wheel kind of looks like this, and you track a point, and you can see that it's going to form some kind of trigonometric function if you follow it up, because the height changes as you go up and down and up and down and up and down, and essentially what's happening is you're following it just like you're following the unit circle. And so this could be modeled by a trigonometric function. Another thing that commonly happens is the height of sort of the ocean, as you've got like a ship trying to go through a dock. And so you can have, like, at night maybe the water level is low, and then at a certain time it rises up to its maximum peak and then suddenly drips back down to the minimum point, and then it goes back up to your normal point. And so this equally could be modeled by a sinusoidal or trigonometric function more generally. And so those are two such examples that you could see, and you'll be able to see those hashed out with more context in your WACE exams and your tests, and also in Sadler. So make sure that you're practicing those. So in this video, we've gone over the unit circle definition of sine, cosine, and tan. A second time, we looked at the concept of periodicity using radians. I introduced that more in the context of graphing, but we did cover that one. We had a look at exact values of sine, cosine, and tan using our God triangles, and we had a look at how we could use those God triangles to extend that to angles larger than 90 degrees or less than 90 degrees as well. We had a look at the graphs of trigonometric functions like sine, cosine, and tan on extended domains and also on restricted domains. We then had a look at amplitude changes when we introduce a variable a and change that variable. That can have impacts on our amplitude of our function. Finally, we have our period b, like this. We have our phase changes. These are all transformations to our trigonometric graphs. And when we introduced the concept of phase changes, we could see that there was a relationship between our sine and cosine graphs that look like this. We also had a look at the angle sum and difference identities. I didn't actually prove it, but this is given in your Sadler textbook. We also had a quick look at some examples that could be used, that could be modeled by trigonometric equations. And those are provided in more detail in the Sadler textbook and will be questions that you'll have to answer, usually in the calculator assumed section of your WACE exams. Alright, so thank you very much for watching. Make sure that you subscribe so you don't miss any new videos. Comment if I've missed anything within this topic, or if you don't understand something. And I wanted to let you know that the next video will be releasing on the 5th of November. Thanks guys. See ya.